This is an overview of chemical reactions, and in order for a reaction to occur, the chemicals have to collide in some way. The collision has to be in a proper orientation and with enough energy to make the reaction occur. So, if this collision theory is correct, then temperature should affect how reactions occur. And if you think about increasing the temperature, then things are going to start moving faster. Moving faster means you can increase the reaction rate by having more collisions. Think about if at the bell everyone had to run to class instead of walk. You can also decrease collisions in the same way. If you slow things down by lowering the temperature, then collisions would happen less frequently. They wouldn't have as much energy when they collided, and reactions would happen at a slower rate. In fact, this is why we keep things in a refrigerator to keep from spoiling. Spoilage is a chemical reaction, and keeping things at refrigerated or freezing temperatures helps reduce the likelihood that that will occur. Concentration would have the similar effect. If there were more chemicals in a given space, there would be more collisions and therefore more reaction rate and faster reactions. If you decrease the concentration, have more liquid in a solution than chemical, then the collisions wouldn't happen as frequently because they'd be harder to find each other. Again, think of how things happen at a train station in, say, New York City at rush hour, where you have lots of people moving quickly trying to get to their trains versus a train station where it wouldn't be quite as crowded. So, increasing concentration would have more collisions, decreasing concentration would have fewer. Surface area as well, if you expose more of the chemical to be able to be attacked by another chemical or collide with another chemical, then the reaction can occur faster. And if there's sort of an insulated area, let's say if you're trying to react to something that looks more like an M&M, the inside of the M&M really can't react until the outside does. So you would want to crush that up so that there's more available to react. That is actually why we chew food, is so that the food can be have greater access to the chemicals for digestion. And just another visual for this, if you think about what cotton candy is a very high cotton candy is a high surface area sugar. So here raccoons like to wash their food before they eat it, and that cotton candy just dissolves in the water because it's so much surface area in cotton candy. So there's that. All right, getting back to this. Um, these are some symbols that we use for reactions. The S means that something would be a solid. The L means something would be a liquid. The G means something would be a gas. And the AQ stands for aqueous, which means it's dissolved in water. And we use these as indicators for a reaction so that you can know what phase different chemicals would be in. So if you took, for example, um, baking soda, which is a solid, and mixed it with vinegar, which is an aqueous acetic acid. Vinegar is acetic acid dissolved in water. You would have the AQ to let people know that that's dissolved in water. You would have the S to know that's a solid. This will release a gas when they're combined. Um, so you would have the CO2 gas. It releases water, which is a liquid. So you'd have the L to let everyone know that was a liquid. And then you would have sodium acetate as well, which is also aqueous. So you would have all of those things to show what state of matter everything was in. So I'm going to erase all this so we have room for the other thing. All right, so that's why we have those symbols. And then arrows as well. We have an arrow one way officially means yields, but basically that a reaction would only go in one direction. If the reaction can go in both directions, we say it's reversible. And then plus just means you're adding things, right? You just saw that I was had carbon dioxide plus water plus sodium acetate. So it just means you had things on both sides. This delta means it's a change. It can be used for a change in temperature, meaning heat, or we'll talk about other things as the semester goes on. All right. So if you have hydrogen and oxygen and you combine them in the proper ratio, you need a little activation energy to make a reaction occur where it'll turn into water. At the end of the day, the hydrogen and oxygen have more energy than the water, and that's why this is a very exothermic reaction. There's a lot of energy given off. So to show you an example of that, we can get into this video here. All right, so what happened here is he bubbled hydrogen and oxygen gas into water. And so that hydrogen oxygen mixture is in those bubbles. And by adding this little bit of energy, what you're going to see is it's going to release a lot more energy than he's putting into it. So here it is in slow motion. So you can even see how that sort of blew her hair from the force of that reaction. All right, so that's exothermic. Um, it still required a little bit of activation energy, so there was some energy to get it started. We call that the activation energy. To get, he had to use that little flame to get it going. Okay, so exothermic reactions will produce energy, and endothermic, which is the opposite, will require energy, and it's the same amount of energy if you think about it. So if he produced water there with that explosion, if you start with water and you want to turn it into the gas, you're going to have to put energy in. So activation energy is going to be required again. You get up to what we call an activated complex, a point where the chemical can either fall back to its starting or move forward to its product. And you can see the energy difference is the same in both the exothermic and the endothermic. It's just in one way the energy is released, and in the other way the energy is required to get up. Um, if we again take a look at a video of this, and we did this in class, where if you're separating water into its component gases, you need this battery energy to get in there. And then you can see that the gas is being produced when the battery is connected to the water to make hydrogen and oxygen gas. Right. So this is the hydrogen because there's twice as much as the oxygen. All righty then. So moving on. So what a catalyst does, as you can see here, a catalyst would lower the activation energy. So especially for an endothermic reaction where you have to put energy in, this is helpful because you can get to those products without having so much energy put in. And you may be familiar in biology with the idea of an enzyme or a protein catalyst. So these do that job of making a reaction happen easier by lowering the activation energy. If you want to consider how that happens, if molecules or chemicals have to hit with a certain orientation and with a certain amount of force, what a enzyme or a catalyst can do is situate those chemicals so that they're lined up perfectly. So think here when H2 and Cl2 have to come together to form HCl, you want the H and the Cl lined up. And so what the catalyst can do is sit those things in a position so the orientation is proper for the reaction to occur. And by doing that, it lowers all the randomness that needs to occur and the reaction can happen with less energy. And if we look into that here real quick with this FET, okay, so here I have, or I don't have anything apparently. This I don't want. All right, so here's a reaction that's occurring. If you increase the temperature, things move faster, right? So, and the reaction can occur. And if the catalyst is going to decrease my, which I can't do thanks to this. All right. I wish I could make this go away. That's not going to happen. But anyway, if I can decrease the activation energy required, there it is. I just needed, now more things can happen. So that's what a catalyst does, is it decreases the amount of energy needed to get over that hump. All right. And the law of conservation mass says mass can neither be created or destroyed by an ordinary chemical reaction or physical change. This means that the reactants after a reaction have to equal the same, or the reactants before you put the reaction together have to be the same mass as the products at the end of a reaction. So when you burn a piece of tissue paper, which I did in class, because the carbon dioxide is formed, if we actually captured that carbon dioxide, it would weigh the same as the oxygen and the tissue before. But so it doesn't go weightless. There's has to be a mass accounting, and because of that, we have to take into account balancing reactions. So if you had a closed container and the chemicals before reacting had a certain mass, after the reaction took place, you would have the same exact mass. Imagine just that the container is closed so that nothing can escape. That would be the case. All right.